So guys, we'll just take, so no questions? Anyone? No? We'll go into our first tutorial, so it's mechanical basics. So it's again, training course, FEA course, this is the first page that you'll see. Click on mechanical basics, it will take you to the course page. And the very first simulation on the far left is called mechanical basics. Click on that and you'll see a folder called mechanical basics, and download that folder. It will have a step model, so a geometry model, and also a step-by-step tutorial. We'll go over the step-by-step for the very first one with Sam on the screen, and then we'll kind of let everyone go at their own pace afterwards. So everyone just make sure they download that, and if you have any troubles, again, just chuck your hand up.
Okay, so don't start this workshop just yet. I'll go through it just so it's easier for you to follow, particularly if you haven't used the software before. Some of you might find it a bit difficult to get started. Okay, so all right. So basically, the component we're analysing is part of well, there's other components that are involved. So this is a cover that's bolted to something else. So because we're only interested in a certain part of this structure, so which screen are we on? Why is this?
What are you going to do?
Okay, that's better. Alright, so we're only interested in the stresses sort of around here, let's say. So we don't need to model the bolts or the other part of the structure. But we do need to replicate or simulate the effect of those other parts. So here we'll make some simplifications in doing that. So what we'll do is we'll use what we call frictionless supports. So these don't allow movement into or out of the face that we define that support on. So underneath where the bolt heads are, so because these are probably torqued down, so we don't expect that face to move into or out of that face. Okay, so it's probably over constraining that face or over stiffening, if you like. But that's going to give us higher stresses than is more realistic, which is what we want. We don't want it to under-predict the stresses. So on the underside of the cover, there's two faces where it seats or mates with the other component. So here we're using a frictionless support to do that. Okay, and then we've got an external pressure on the outside of the component. Okay, so to start the software, so this might be a little bit different on the computers here. So it's ANSYS 18.1, and then at the bottom you go to Workbench. Okay, so this will start the Workbench interface. All right, so your screens might be a little bit different to this. So this is basically all of the predefined systems or analysis systems that you can simulate using Workbench. So they're colour-coded. So the red ones are basically thermal, green ones are basically structural, blue ones are for fluid flow or CFD, and then there's orange ones that are used for doing electromagnetics or when you're simulating voltage and current. Okay, so normally what we do is we choose what we want to do. So in our case, we want to do a static structural simulation. So you either double click or you drag and drop. If you drag and drop, it has to go in the green box. If you double click, it will put it in the first available slot. Okay, so essentially to complete our simulation, we want green ticks on all of these steps. So engineering data and geometry, probably the two first things we need. So engineering data, so by default, it will assign structural steel to everything. So if you want to use a different material, so you double click to go into engineering data, and then up the top here is engineering data sources. So this is like a toggle. Okay, so when you first come in, it will show you the materials that are defined for your particular simulation. So at the moment we've only got structural steel. So if I want to make more materials available, I click on the toggle, the engineering data sources, so the 3 books stacked side by side, and then I have to choose from a library. So if you like, this engineering data sources has a whole heap of different libraries of materials. So we're going to start off with the general materials. Okay, so do not tick this box in row B. Okay, so that will unlock your library and make it editable. You don't want to do that. Okay, if you want to edit your materials, you have to first bring them into your simulation. Okay, so let's say, for example, I wanted to maybe use magnesium alloy or aluminium alloy. Okay, is this picking up now? Okay, so, or aluminium alloy, so I tick on the plus. Okay, so now I've chosen my materials, I need to toggle the engineering data sources off. So now I've got 3 materials available to me. Okay, so in my simulation I can choose to use any one of those 3. Okay, sorry, I've lost where I was now. What the hell? Okay, so don't worry too much about following along as I'm doing this. You'll have adequate time to do it when we're going through. Where's it gone? Okay, so I'll just repeat that quickly because I seem to have lost my... Okay, so this is a toggle, this engineering data. Okay, so I go to general materials, so I'll just select one material to make it simple. Okay, so now I need my geometry. Okay, so here in this case I'm going to import geometry. So I need to browse. So this will be the file that is in the zip file that you have downloaded. Okay, so now the geometry's got a green tick. So do not double click on the geometry. We don't need to edit the geometry. So under geometry you right click, wait for a few seconds, and then it will have import, and then you browse to where you've got that geometry.
Once I selected the material, how can I bring it to the workbench?
So if you just click back on the project tab, it will go back to the project.
So how do I know that the material is selected?
It's not yet. You haven't assigned it. So just watch me go through this first,
Yep.
and then we'll let you go through it at your own pace. If you've got any questions as you're going through, we'll come around and help you. Okay, so on the outline, that's basically my project tree. Okay, so here under the parts, in the details of the part, there's a material assignment. Okay, so because I've got aluminium alloy in my material properties as well as structural steel, I get it as a choice. So if I want to assign a different material, yeah, so if you've linked the geometry, so to start it up, you've got to double click on the model cell. Okay, so with the mouse controls, so basically I'm using the middle mouse button to rotate the model around, and then you use either control or shift to sort of zoom in and out. Okay, so basically I'm going to work my way down through. Okay, so don't try and follow as I'm doing this, because we'll give you adequate time to do it. So if you've seen it done once, it will make it a lot easier to follow when you do it on your own. Okay, so here with the mesh, so if I right click, generate mesh, okay, so depending on which branch I click in, the menu item here at the top will change. Okay, so there's two ways we interact with the model. So the first way is to select the branch, then you can either use the bar across the top, or you click in your geometry window, you right click, and then you get this insert menu show up. So normally the workflow is you select something in the geometry, and then you right click, and then you choose what it is you want to do with that geometry. So for example, if I go into static structural, so you see how it's got a question mark. So it's got a question mark because there's something not complete yet. So if I click on the mechanical wizard, so this sort of walks you through the steps and also where to go on the user interface to find things. Okay, so there's a cross on structural loads because there's nothing done yet. So if I click on insert structural loads, it flags me where to go. If I click on this drop down menu, these are all the load types that I can apply. So because I know that I want to apply pressure, I can choose that from there. Okay, so I won't do that just yet. Okay, so likewise with supports, it tells me where to go to apply my supports. Okay, so probably the easier way to apply loads and boundary conditions is by first selecting the face. So let me start from that bottom face there. So I'll right click, insert, and then choose what I want to do with it. So in this case I'm going to do a frictionless support. Okay, so my second set of supports, so I'm holding control down and I'm moving the model with my middle mouse button. Okay, so I don't really want to have to do that all the time if I'm selecting multiple faces. So basically I select my first face and then I say extend to limits, and it finds all the surfaces that are in a tangent continuous loop. Okay, so here I'm also going to insert a frictionless support. Okay, so now on the top, okay, so here I'm going to select the four faces where the bolts would be touching, and I right click, insert frictionless support. Okay, so you notice it's still got a question mark. So if I wasn't sure why that question mark was there, I can click on show errors. Okay, here in the message it tells me you need at least one structural load to proceed with solution. Okay, so because I've only got supports and no loads, it doesn't make sense to try and solve this model yet. Okay, so until I correct that, I can't solve the model. I can try, but it will immediately come back. You need at least one structural load to proceed. Okay, so I click on the top face. So I want to basically take all of the outer faces of this cover. So if I say extend to limits, so I've got my faces selected. So down the bottom there it says 17 faces. So I right click, insert, whoops, and make sure I'm in the static structural branch. So when I right click, insert, it brings up things for loads. So here I say pressure. Okay, so now in the details view, I need to put in a magnitude. So this will be based on the unit system that I'm working in. So it's millimetres, so it will be megapascals. Okay, so now I can say right click, solve from down here, or I press solve in the main menu there. Okay, so that will go away and solve the model. So it's not a very complicated model, so it should be fairly quick to solve. Okay, so once the solve is complete, so I can right click, insert, total deformation. So I could also put these in before I start solving, so that then I've got results straight away. And right click, insert, equivalent stress. Okay, and then I evaluate all results. And then if I look at the total deformation, okay, so I can animate this just to make sure it's deforming in the correct sense. So this, in this particular case, it makes sense that it would deform and deflect in that way. Okay, so we've got equivalent stress as well. So if you sort of zoom in, or sorry, show the max and minimum, you can see where those particular areas are. Okay, so I've got the maximum stress on that sort of that fillet there. Okay, so if we wanted to make sure that our results make sense, so we'd look at the total reactions or the reaction forces. So a lot of things inside Workbench or mechanical are all about drag and drop. So if I want to find out what the solution is of this frictionless support, that would be the reaction force. Okay, so if I select the three frictionless supports, I drag and drop. And then if I just right click on one of them, evaluate all results, it will tell me what the reaction force is. So here for that particular support, that's the reaction. Okay, so there's the other reaction there as well. So on the bottom face here, so in this particular case, because of the way this model is, because of the way these frictionless supports have been set up, so this particular face can only really have a reaction in the Y and X directions, but it's got a reaction in Z. So if I zoom in, so because that face, or that edge, is belonging to that face, it's got the frictionless support that stops movement in Z, there's a reaction component that comes from those nodes. So if we were doing a force balance, we would exclude force reaction 2. So what I'm going to do is I'm going to delete that. Okay, so if I sum up my reactions, so I've got 2,850 plus, let's say 1,300, so whatever that comes out to be, 2850. So let's just say it's around 4,000. Okay, so to get an idea of what the total force in the Z direction is, because X and Y will be balanced, because the pressure components in those directions are basically balanced, because there's equal area in those directions. but there's nothing to counterbalance the pressure in Z aside from the supports. Okay, so if I click on this face here, down the bottom there it tells me what that area is. So 3640. So that, and with that in my pressure, I can get a rough estimate of what my force in the Z direction is. So I can then compare that to my reaction in Z, and they're pretty close to being balanced. So, and that's what I would expect. If they weren't, then it's possible that there's something gone wrong with the way I've loaded and constrained this particular model. Okay, so they're probably about the only real checks on this particular model that you can do. So, and they make sense, so that then you can trust that the other results you're getting should also make sense. Okay, so when we're post-processing, so you notice that this contour bar doesn't have very many colours. So because there's a sort of a high stress region on the underside here, that's where all the colours are sort of focused, if you like. So if I wanted to look at the stress just on one particular face, so I click in the solution branch, I select the face, I right click, and then I choose what I want to do with it. So here I'm going to insert stress and then evaluate result. Okay, so now my rainbow is going from 0 to 47 because it's just the stress on the top face. Okay, so I could do the same thing on other faces on the model. So if I wanted to look just in the high stress area, and I say insert stress, and then you can evaluate results. So I can then also probe in that area as well. Okay, so because there's such a large variation of stress across one element there, the mesh probably isn't fine enough. Okay, so so what we can do, so this isn't part of the workshop, but it's something that I can help you do if you're interested after you've done the initial solution. So what I can do is I can insert a convergence, and I tell it I want a 10% change. So what it will do is it will refine the mesh. So I'll tell it to do 3 loops. So it will refine the mesh just on that face until the difference between the stresses between 2 successive runs is less than 10%. So that will make sure that my mesh gives me a converged, in terms of converged on the stress result. Okay, so it'll go away, it's done 1 loop. Okay, it's been a 16% change. And you'll notice how it's refined the mesh. So it's now refined the mesh again because it wasn't 10%. Okay, so I've just missed out, so it's 10.1. So it will now do a third loop. So usually with these elements, if you can't get convergence within 3 or 4 loops, then it's highly likely that you've got a very high stress concentration there. And the FEA solution will approach the theoretical solution. So if it's an infinite stress concentration, that's what the FEA solution will tend to. Okay, so here it's got a 3% change, so it's got a converged result. Okay, so if I look at my stress there, so if I probe across 1 or 2 elements, you can see that there's a much lower percentage change across one element. Okay, so you generally don't want to make your mesh fine everywhere to capture that level of detail, And certainly in a case like this, if you did try and do that, then you would wind up picking up a stress singularity somewhere. So you can do this convergence on a global result, but it's generally not recommended because it will always pick up a stress singularity, and there will always be one somewhere on your model, either because of the way it's been supported or because of a simplification to the geometry that you've made. Okay, so one of the other things that you may need to do, so I didn't do it on here because I don't need to. So as soon as you've brought the geometry in, save the project. Don't save it on your network drive because it will not solve, or possibly not solve. So I think there's a D-temp, so save your projects there initially. So if you want to keep these after this course is completed, so once the model you're finished with the model, you can do a save as. So just while you're solving, because it has to write temporary files to the same location as the project, if that's on a network drive, and if it does actually let you solve, it will be very, very slow. So you want all of the disk activity to be between the local hard drive and the CPU that's on your machine, because otherwise it uses the network bandwidth rather than the local disk I/O inside your machine, and there's a factor of a few hundred difference in those two. Okay, so that concludes the demonstration. So